So good afternoon. Today we're going to finish up the supervised learning part, so this will be a bit shorter. Also this week there are still tests, so I'm not going to give too much, to advance too much on the subject matter. So this is basically to wrap up the supervised learning part of this course, and we're going to look at some theoretical aspects that give a better grounding to some intuitions we've been developing along this first part. So previously we saw the bias-variance trade-off and how we can avoid overfitting. We also saw that in practice, how to avoid overfitting by validation and cross-validation, and so try to adjust either the training of our model by regularization or selecting the best model by using cross-validation or some meta-parameters. But today we're going to understand these issues a bit more formally. So we're going to look at empirical risk minimization and to get a more probabilistic notion, more formal notion of these problems, and see this notion of probably approximately correct learning, which is actually what we've been doing all along. And then we're going to see these for models with continuous parameters, this notion of shattering and the Vapnik-Chevronenkis dimensions to try to evaluate the power of a classifier. So this will be a bit shorter than usual, the lectures today, but especially this part will be a bit denser because of the more theoretical framework. But the idea is not that you know how to do these demonstrations and so on, but to understand some of these notions that we saw so far, why they are theoretically important, and to get a better intuition about this. So let's start with empirical risk minimization. This is basically what we've been doing, only we haven't been calling it that. We start with this notion that we have some loss function that can measure how bad our predictions are. So we used, for example, the quadratic error when we did regression, or we use the Breyer score for logistic regression, or the 1- accuracy for classifiers in general, so the error rate of the classifier. So basically we have this idea that we can measure how bad things are going, and this will be the loss function. The risk is the expected loss, so we can measure our risk by what on average the loss will be. In general, we don't have access to the overall risk. So the true error, for example, we cannot do experiments with all the possible data, but we have this empirical risk measure. So this is the average loss we can measure on the training set, for example. And empirical risk minimization consists in trying to select the hypothesis that minimizes this empirical risk. That is, it minimizes the measured loss on the training set, which is basically what we've been doing, minimizing, for example, the error on the training set. As we're going to see later, the notion of loss can go beyond simply error. We can take into account other things. There is also this true risk or true error, which is the risk of misclassifying things over all possible data. We don't have access to that. We saw some ways of trying to estimate this with validation, for example, with testing, keeping some data outside of the training set so we could get an estimate of this. But today we're going to see the relation between the empirical error we're measuring on the training set and the true error. We know that this error we're measuring on the training set is a biased estimate because we are selecting the minimum error. But we can also find that there is a relation between this error and the true error. So it can give us some boundaries on what the true error would be. So this is what we're going to see here. We're going to look at some probabilistic relations, starting with this union bound. So the probability of, we have this set of k random events, and the probability of at least one of them occurring is less or equal to the sum of their probabilities. So if they are mutually exclusive, the probabilities are equal, so the probability of at least one of them occurring is the sum of the probabilities. But if they are not mutually exclusive, the probability of at least one of them may be less than the sum of their probabilities. In any case, we have this bound on the probability of any one of them, or at least one of them occurring. We also have this Hostings inequality, which tells us that if we have these independent and identically distributed Bernoulli variables, these Bernoulli variables are yes or no with some probability. So basically, we can use that as the probability of making a mistake in classification, for example. And if there is some probability of making that mistake, for example, then and if we measure the probability of that, the frequency of that event over a finite sample M. So this phi here with the little hat is what we actually measured, and this would be the true one, the true probability of that event. So in that case, the difference between the probability of the event occurring and the measured frequency with which it occurs in our training set, for example, in our data, the data that we can examine, the probability of this difference being more than some gamma value is less than or equal to twice e raised to, so the difference between the two is less than or equal to 2 times e raised to minus 2 gamma squared m. So basically this is a bit of a confusing formula, but the idea is that the probability of the measured error rate deviating from the true probability of error, so this would be our empirical error here, and this would be the true error over all the possible data. The probability of the difference between these two being greater than gamma will decrease as we increase the size of our training set. So if we increase m here, the larger the data points we are looking at, the smaller the probability that this will go outside this interval. Of course, this probability also depends on gamma, so if you want to increase gamma or decrease gamma, we're going to affect all these probabilities. So this, we're going to use this to try to relate the empirical error, the one that we actually measure on our data set, and the true error, which would be the true probability of making some mistakes. So suppose we have these binary classifiers with some parameters theta. We find the best set of parameters by minimizing the empirical error. So this is the error that we're actually measuring, and we are finding one hypothesis here as a function of this theta that minimizes this error. And this gives us the best set of parameters. So this is empirical risk minimization, because we are measuring the risk empirically on the training set and finding the parameters that minimize. In general, this is an NP-hard problem, but we usually approximate it with those learning algorithms, for example, backpropagation in neural networks, those minimizations we use for regression and so forth. So we use some methods to try to make this a bit more efficient and approximate the correct value, although we generally cannot guarantee that we don't get stuck in a local optimum or something like that. And now we can use Hostings inequality to try to find a boundary or probable boundary on the true error based on the empirical error that we measured. So this is the notion of probably approximately correct learning. The idea is that we have some set of possible data, so this is where our possible instances can come from, that large X there. We want to learn a function that classifies each point into class 0 or class 1. We have this hypothesis class from which we're going to draw one of the functions that we think is the best one. And there is this distribution D, which is the probability distribution when we sample from this possible set of data points. So when we draw from that possible set of data points, maybe not all the values are equally probable, there is some probability distribution, but we're going to assume that this distribution is always the same. And we have this training sample which we drew from the possible set of points with that distribution. Now we're going to give this sample to our learner. We drew that sample from X with this distribution D, and our learner will select one hypothesis from our hypothesis class by minimizing the empirical risk. So it's going to choose one hypothesis by measuring the risk or the average loss on the sample that we gave it, and it's going to go through many different hypotheses and pick one that minimizes that risk. We're not going to worry about the algorithm. This is all very abstract, but we're going to assume that we can pick one hypothesis that minimizes the risk. Now, this would be the true error of an hypothesis, which is the probability of getting an error in all the data. But this is not exactly the same as the empirical error of the hypothesis. Sorry, I skipped one slide here. Okay. So there is not, we cannot guarantee there is a complete overlap between the hypotheses that have no empirical error and the hypotheses that have no true error. There may be some difference there because we are only measuring on a small sample on our training set. So the true error would be the actual probability of that hypothesis making a mistake, but we cannot observe that directly. What we can measure is the empirical error or the training error, the error that we measured when selecting the hypothesis. So this is actually this average of our loss function, or counting in this case 1 when we misclassify and 0 when we classify correctly. So it will be the average classification error rate here. Well, not overlap, but we'll minimize the probability that their difference is greater than some value. So they may never exactly overlap, but we can set some bounds on the probability that they differ for more than some epsilon value. So this is basically what we can measure, the training error, and this would be the actual true error, the probability of making a mistake, but we cannot reasonably demand that the best hypothesis that we have has a 0 true error. So that's not very reasonable because we don't have all possible examples in our training sample. It's limited, and so there may be several hypotheses that minimize the empirical error, but some of them make mistakes outside the training set. And the examples also may be misleading. There may be some examples that suggest this hypothesis is best, but they are not very representative of other examples that are in our possible, in all the set of possible data. So this is what how we come to this notion of probably approximately correct learning. We cannot guarantee that there will be this complete overlap between the empirical error and the true error. So what we have is that we have the best hypothesis, we want it to be approximately correct. That is, the hypothesis that we chose minimizing the empirical risk has a true error below some epsilon. So this is what approximately correct means. But not even this we can guarantee with absolute certainty. So what we're talking about is that we get a probably approximately correct hypothesis, meaning that the probability of the true error of the hypothesis being below this epsilon is greater than 1 minus some delta. Or putting it the other way, the probability of the true error going above the epsilon is smaller than this delta. So basically we are putting an upper bound on the probability of making a larger error than that epsilon. And this is what is probably approximately correct means. This is what we're trying to realistically obtain when we train our models, or when we find our hypothesis. We are trying to make it probable that the error, the true error, is not very large. Now, let's start here with some assumptions that the hypothesis space is finite, and it contains hypotheses with true error below epsilon. Of course, if this doesn't happen, then we cannot have any hypothesis with true error below epsilon. And also, we are always drawing all our samples from this distribution D. So the distribution never changes. And now we can try to use this notion to find a relationship between the training error and the true error. So let's start with some definitions here. A consistent hypothesis is one that classifies the training set without making any mistakes. So the empirical error is 0. This does not mean that the true error will be 0, but at least with the data that we have, the error is 0. And the version space is the set of all hypotheses that are consistent with our training set. So version space for some set is a set of all hypotheses which have an empirical error of 0, meaning that it's the set of all hypotheses that can classify our training data without making mistakes. Now, a consistent learner is one that outputs hypotheses in the version space. That is, we have some learning algorithm that can select an hypothesis that makes no errors in classifying the training set. So when we minimize the empirical risk or the error in the training set, we get something that makes no mistakes in the training set. It may have some true error greater than 0 because it's not looking at all the possible data, but at least with the data that we supply, it's not making any mistakes. And we can say that the version space is exhausted in epsilon or epsilon exhausted if for all hypotheses in the version space, that is, all hypotheses that make no mistakes in the training set, have a true error below epsilon. So this would be epsilon exhausted, meaning that if we take all the hypotheses that manage to classify our training set without mistakes, we will not find any with a true error greater than this epsilon value. But the version space is not epsilon exhausted if there is at least one hypothesis that breaks this. There is one hypothesis in the version space which makes no mistakes in classifying the training set, but has a true error greater than epsilon. Now the thing is, we cannot determine this from our data. We don't know if the version space is epsilon exhausted or not for any epsilon, because we cannot measure the true errors of our hypothesis. But we can try to reason about the probabilities of this happening. So let's consider what is the probability that there is no hypothesis in the version space that has the true error greater than epsilon. Let's suppose that we have a set of hypotheses in our hypothesis class that have a true error greater than epsilon. The probability of any of these hypotheses, of each of these hypotheses being consistent with one example, is less than 1 minus epsilon, because this is the probability of making a mistake. So if that is the probability of making a mistake, if we feed it one example, it can make a mistake with that probability. So it's consistent with the probability 1 minus epsilon. That is the probability of not making a mistake with one example. If we give it m examples, and it must not make a mistake in any of them, then the probability of not making a mistake in any of the m examples is 1 minus epsilon raised to m. So this would be the probability of an hypothesis that has a true error greater than epsilon, because that's the probability of making a mistake. So this is the boundary on the probability of it being consistent with all the examples in the training set. It cannot be larger than 1 minus epsilon raised to m. So the probability of there being at least one hypothesis that has a true error greater than epsilon, but it's consistent with all the examples, must be below k, which is the number of hypotheses that have a true error greater than epsilon, multiplied by the probability of one of them. And the reason for this is that probability of the union, so any one of those events occurring, cannot be greater than the sum of the individual probabilities. So this gives us a boundary on what would be the probability of finding a hypothesis that has a true error greater than epsilon, but it's still inside the version space because it makes no mistakes on the training set. So we don't know how large this k is, because this is the number of hypotheses that have true error greater than epsilon, and we don't know what the true error is. However, we know that k cannot be larger than the size of the hypothesis class, because that's all the hypotheses that we have. So we can get this upper bound here, k times 1 minus epsilon raised to m must be below or equal to the number of hypotheses in our hypothesis class multiplied by that factor. So we can do this simplification. 1 minus epsilon is less or equal to e raised to minus epsilon for all epsilon between 0 and 1, which is the case here because it's a probability. And we can simplify this to the number of hypotheses in our hypothesis class raised to e multiplied by e raised to minus epsilon m. So basically, this is the probability boundary on there being at least one hypothesis in the version space with a true error greater or equal to epsilon. This probability cannot be greater than the total number of hypotheses that we have multiplied by e raised to minus epsilon m. Now, if there are no hypotheses here in the version space with a true error greater than that, and our learner is consistent, it gives us one hypothesis in the version space, then in that case we are safe. No hypothesis that we'll get from that learner will have a true error greater than epsilon. If this doesn't happen, if there is at least one hypothesis there with a true error greater than epsilon in the version space, then we don't know. We may have bad luck and get that hypothesis. So we can go from this probability that we wanted to estimate, the probability of the hypothesis that we picked with our consistent learner having an error below epsilon. We can assume that this must happen if there are no hypotheses in the version space with a true error greater than epsilon. So we can replace that here. We can call that delta, and now we can get an idea of how large our training set must be in order that we can have this probability of delta being the probability of the hypothesis we get from our learner having a true error larger than epsilon. Or, to put it the other way, the probability of having a true error below epsilon being greater than 1 minus delta. So if we replace that there, this is the expression that we have. So basically, if we want the epsilon to be small, we have to increase the size of our training set. So this is the generalization error, which is, we are assuming that we have a training error of 0, so the true error will be the difference between the training error of 0 and the true error. If we want that to be small, we need to increase our training set. Also, we need to increase our training set if we increase the size of our hypothesis class. Only in that case it's with the logarithm, and this is for a fixed probability delta. If we also want to decrease the probability of having this true error outside epsilon, we also have to increase our training set. So basically this gives us this intuitive notion that the larger the training set, the more probable it is that we'll find a hypothesis with a true error below some small value. Assuming that we can train, that we can find a hypothesis that makes no mistakes in the training set. Okay, so this was our assumption from the beginning. Also, if we have a hypothesis class that has more power to fit our data, that has more hypotheses there, then we also need a larger training set in order to keep our true error down. So this is basically, note that this is a very large boundary because we have been making these safe assumptions about the probability. So in practice, we are not going to use this to actually estimate the true error because this will overestimate. It's a very safe boundary for these probabilities. In practice, it's much better to use a test set or something like that and get an estimate, an empirical estimate of the true error. But this gives us a stronger theoretical grounding on these intuitions, that if we want the true error to be small, or if we want to be pretty sure that the true error is small, we need to increase the training set. We need a larger training set. Also, if we use a hypothesis class that has much more room to adjust to our data, we also need a larger training set in order to avoid the error increase. Okay? So this would be an upper bound on the error with respect to m, or with respect to, so this is a lower bound on m, or an upper bound on the error with respect to the size of our training set and the probability delta. So again, if we want to get this error small, we need to increase our training set. Now, this assumes that the hypothesis we get with empirical risk minimization has an empirical risk of 0. That is, we can classify everything without any mistake. But we can extend this for the cases where we don't have an error rate of 0 on our training set. So this basically just means that we can use the same hosting inequalities because we still have these Bernoulli variables. This would be the error measured on our training set. It's merely the number of mistakes we made divided by the size of the training set. But now the difference is that this epsilon, it's still a generalization error, but now we have this the training error here too. So we are trying to find this epsilon, which is how much the true error goes over the training error that we found. And basically the equations are the same, but now we can use this expression and decompose those relationships in a different way. So this would be for one hypothesis. For all the hypotheses here, we would get this, the size of the hypothesis space times e raised to minus 2m epsilon squared. We can also solve again for delta and for m, so by replacing there, and we get this lower bound on the size of our training set to ensure that we only have a probability delta of the generalization error being epsilon or greater. So this generalization error is the difference between the training error and the true error. So note that this increases quadratically with 1 over epsilon and also with the logarithm of the hypothesis space. So here we can look at this initial idea that I talked about, the inductive bias. It's not the same as the bias on bias and variance, but it's that bias we get because we restrict our hypothesis space to something like hyperplanes in n dimensions or things like that. So we don't consider all possible hypotheses, but we bias our hypothesis space to specific constrained subsets of all possible hypotheses. And here we can understand why we need to do that. We cannot have learning if we don't do that. So let's suppose that we have, as a hypothesis space, the set of all possible subsets of all our possible data. So X is the set of all possible points, and our hypothesis space is all subsets of that. This means that we can classify anything in any way, because there is always a subset of X that will be in one class, and the rest will be on the other, and our hypothesis space includes all possible combinations of all possible data points. So if that is our hypothesis space, and let's assume, to simplify, that each X is a vector of n Boolean features. So they are only 0 and 1, but in principle we can represent everything as a set of Boolean features, otherwise we couldn't use the computer to work with it. So it's a set of bits, each of our points in the X set. This means that our hypothesis space must include all subsets of X. So the size of the hypothesis space is 2 raised to the size of our possible data points, and the possible data points that we have is 2 raised to n, because each data point can have n bits of 0 and 1. So this would be the size of the hypothesis space. If we put that in our expression, we see that in order to have only a delta probability of having a generalization error above epsilon, we need to have an m greater than this. But the hypothesis space is 2 raised to 2 raised to n. When we do the logarithm, we get the base 2 there, and we can put 2 raised to n as a multiplier here. And this 2 raised to n is the size of all our possible data. So we cannot have more deep points than this, because they have n bits, and this is the combination of all n bits. This will typically be greater than 1, because we want a relatively small delta, about less than 0.5 certainly, and this also because we want a relative error less than 0.5. So what this tells us is that, according to these bound estimates, we will need a training set that is larger than the possible number of points we can have in all the universe of our data points. So this is clearly impossible. If we don't have any bias in our hypothesis class, then the error explodes and we cannot really extrapolate from the training set to all the other points. Okay? So this is a more probabilistic and formal demonstration, let's say, that we really need to have inductive bias. So that's why we use, for instance, linear classifiers. We have an hyperplane, and we strongly reduce the possible set of hypotheses that we can use. Another thing that we can look is look at the generalization error for the empirical risk minimization hypothesis, where the generalization error is the difference between the true error of the hypothesis that we chose and the empirical error of that hypothesis. So this is how much we increase the error when we go from the training set to everything else. And we have this learner that gives us this hypothesis that minimizes the empirical error. So this is what we do when we train anything, the model, etc. And now let's call this H star. Let's say this is the best hypothesis that we have in our hypothesis class. It means that this is the hypothesis that minimizes the true error. This is not a hypothesis that we can find because we cannot measure the true error, but we can assume that there is some hypothesis in our hypothesis space that would have been the best one. That one minimizes the true error. What we get is the one that minimizes the empirical error because that's all we can do. So we can use this expression that we saw before. So basically, the probability of the true error being below the empirical error plus some epsilon is greater than 1 minus delta. This is what we want here. And we also know that the empirical error of the hypothesis we chose must be smaller or equal to the empirical error of the best hypothesis. This is because we are minimizing the empirical error, so if the best hypothesis had the smaller one, that would be the one we had chosen. So we can join these two together, and we know that the true error of the hypothesis we chose is less than the true error of the best hypothesis plus twice the epsilon, with at least this probability 1 minus delta. Now we can do everything that we saw before with those all those expressions, and we can decompose this into these two terms. So basically, the true error of our hypothesis will be the smallest possible true error in our hypothesis space, so the true error of the best hypothesis, plus this expression which includes m and the size of our hypothesis space. And we can see this as analogous to the bias variance decomposition. So when this term dominates, it means that the true error of the hypothesis we're getting is large because our hypothesis space does not have any hypothesis there with a true error that is very low, because we get always large true errors in any hypothesis in our hypothesis space. So this is what happens when we are underfitting and when bias is very large. Because there is, in our hypothesis space, there are no really good hypotheses that we can get with a very small error. When we have the other situation, when this error is small, so the best hypothesis in our hypothesis space can have a very small true error, but this is large, typically because we have a very large hypothesis space for our training set. This is what happens with overfitting. So we can get a very small empirical error. There are some very good hypotheses in our hypothesis space, our hypothesis class, but we are very likely to get one hypothesis that, even though the empirical error is very small, the true error is very large because of this term here. There are many hypotheses to choose from, and we can choose one that is not ideal. So this is what happens when we are overfitting. So basically, we can find in these error boundary 2 this idea that there are two sources of error when we are minimizing the empirical risk. On one hand, the inability of our hypothesis class to have a really good hypothesis, and this can increase this part here. That happens when we are underfitting, when we don't have a good hypothesis class for that kind of data. Or the problem of having too many hypotheses. All of them may have a very low training error, but some of them or many of them have very high true error, and so we pick one that is not the best one. So this is the one way of understanding probably approximately correct learning when we assume that the hypothesis space is finite. So that was one assumption so far. That's why we can use the size of the hypothesis space. Of course, it happens in many cases that the hypothesis space is infinite because we have continuous parameters and we can put anything there. And if that happens, that expression is not very useful because then it's still true that if we had that training set, we would guarantee that the probability of having epsilon greater, or the true error greater than that epsilon will still be below the delta. But it would be a very bad boundary for that because it will be infinite there on the M2. So when the hypothesis class is infinite, we have to use a different approach, which I'm not going to detail as much, but we'll have to get some notions about how we can measure the hypothesis, the size of the hypothesis class when this size is infinite. So we need some different measures for that. And we'll start with this notion of shattering. We can see that when we have continuous parameters, many hypotheses are equivalent when it comes to classification. For example, if we want to separate these two classes, we can put lines anywhere here, and it will give always the same result. So counting the number of lines is not very meaningful. So instead of that, we're going to use this measure, this notion of shattering. So we say that a hypothesis class H, which may be infinite, it may have continuous parameters, shatters a set of F points if for any possible labeling of these points in the two classes, there is at least one hypothesis there that can separate the two classes without making mistakes. For example, if the hypothesis class is a straight line, is the set of all straight lines, so this is an infinite hypothesis class, we can find 3 points for which there is always at least one hypothesis that can classify them, regardless of how we put the class label. So if we put red here, blue here, and here, we can find this line. If we switch red to that side, it's this one, or if we put everything blue or everything red, we can also find lines for that. So it's possible to shatter 3 points with a straight line. That is, we can find a way of placing 3 points so that any combination of labels can be classified by a straight line without mistake. So this is the idea for the notion of how we can measure the power of a set of hypotheses. In the case of a linear classifier in 2 dimensions, if we have 4 points, then there is no way of placing the 4 points in order to allow them to be shattered by a straight line. Because in any configuration that we put the 4 points, there are always some combinations of labels that we cannot separate completely with a straight line. For example, this one, we cannot find a straight line that will classify them without mistakes. And we can rearrange the position of the points anywhere that we want, and there is no way that we can place the 4 points so that any combination of red and blue can be classified without error with a straight line. So a straight line, a linear classifier in 2 dimensions cannot shatter 4 points, but it can shatter 3 points. So this is the idea for the VC dimension, or the Vapnik-Chevronnenki's dimension, which is a measure of the ability of some hypothesis class to classify. And this would be the size of the largest set of points that this hypothesis class can shatter. This is the VC dimension of the hypothesis class. Note that there may be sets of points below the VC dimension with less points than the VC dimension that the hypothesis class cannot shatter. For example, if you place 2 points, one on top of the other, then we cannot distinguish the two with any classifier because they have exactly the same attributes but different classes. So it's always possible to generate some set of points that cannot be classified without errors. But the idea here is that how large is the number of points that we can arrange so that for any combination of labels we can classify without errors. And that is the VC dimension of a hypothesis space. Now there is an even larger train of deductions here to get to this expression, but we also can find an upper bound on the generalization error here. So with a probability of at least 1 minus delta, we find that the true error of the best hypothesis will be below the empirical error of the best hypothesis plus a term that is on the order of this. So the VC dimension of the hypothesis space divided by the number of points in the training set and then multiplied by the logarithm of that and an expression on the delta that we have here. So basically we can also find an upper bound when we have the continuous parameter, so an infinite size of the hypothesis class based on the Vapnik-Chevanenky dimension. And the idea here again is the same. If we have more powerful classifiers that is able to shatter the sets with a larger number of points, then if we want to keep the same generalization errors, the generalization error low, we need to increase the training set. Otherwise, we get into overfitting because we start increasing the difference between the empirical error and the true error as we increase the VC dimension. So we saw this happen with linear discriminants. A linear discriminant can shatter, if it has dimension d, it can shatter d plus 1 point. So a linear discriminant in 2 dimensions can shatter 3 points. In 4 dimensions, it can shatter 5 points, and so forth. So as we increase the dimensions, as we did, for example, explicitly in logistic regression or implicitly in support vector machines when we use the kernel trick, if we increase the dimension of our classifier, even though it's always a hyperplane, we increase the VC dimension here and we start increasing this term. So eventually we start overfitting because we start getting a true error much larger than the training error. And that's why if we do that, we also need to increase the training set if we want to balance or use other techniques like regularization and so on to try to prevent this from happening. So to sum up this part, this was a bit dense, but the idea is that we're not going to go into much detail onto these aspects, but the idea is that there are many things we do in practice, like checking with validation to see if we're overfitting, using regularization and so forth, that have this solid foundation in probabilistic theory, and we can understand it better if we understand at least the relation between the training error and the true error and these probabilistic bounds. So one important thing here to understand is this notion of probably approximately correct learning. We are not guaranteeing that we are going to train something that will make no mistakes or that will bound the error at some level or something like that. What we can do is train our classifier so that it's probable that the true error will fall below some value or the generalization error will fall below some value. The difference here is that generalization error is the difference between the empirical error and the true error. Sometimes we assume that the empirical error will be 0 because often we can adjust our training set well. So if the training error is 0, then the generalization error is equal to the true error because it's just the difference between the true error and 0. More generally, the generalization error is simply what we add to the empirical error to get the true error. So we can probably keep the generalization error below some value, but that is the best we can do here. We also need inductive bias because if we explode the size of the hypothesis class, then we'll need more points for training than we can possibly get. And we saw the equivalent of that instead of using the size of the hypothesis class, the Vapnik-Chevanenky dimension for continuous parameters or for hypothesis class that are infinite. So here are some chapters to read. Mitchell is a bit outdated, but has some detailed explanation of this part. Basically, it has nothing on the Vatnik-Chevron dimension because these are more recent results. And also you have something there on alpha. And